and it's Peter Barnes. He's online, but we're going to be listening to a recording, and he can answer questions after his recorded talk. And Peter will be giving a presentation on the perspectives on survey astronomy at 3 millimeter, potential niches for the Argus 144 instrument.
Okay, thank you to the organizers for allowing me to present this talk, and I'm just going to get started. So I wanted to originally write a talk outlining some ideas for what Argus and the GBT could do together, but seeing the large number of talks scheduled where people are thinking about specific projects led me to redesign my talk for something a little bit more big picture. So anyway, instead I'm going to talk about some general observing program design concepts and ideas, and how an instrument like this could be most useful to the community and best taken advantage of. And starting with these disclaimers, one of which I just gave you, so this is a different talk than what my abstract might have indicated. So I want to bring my experiences with various instruments and those of others with working on projects to do with those instruments, things that we've learned so that we can apply those lessons a little bit to the discussion at hand. And so this is not meant to be dogmatic or absolutist, but rather just sort of advice for colleagues, as it were. So with help from Yogi Berra on the advice department. Okay, so let's see. One of the first, and you can read the slides here, so I'm not necessarily going to repeat everything in the slides, but rather just try to focus on the big ideas. So one thing which struck me about Argus and some of the observing programs being discussed was the concept of evolution versus revolution. By that I mean clearly Argus 144 would be the best thing of its kind to have been developed in terms of spectral sensitivity and survey coverage and all of those good things. But we have to remember that a lot of this sort of work started a long time ago, and a lot has been done since. So there was, as Dave Freyer said, the FPAs were around for 30 years now, since Quarry. Also, flexible wideband backends have been around for half that time, going back to MOPRA, which is one of the first ones to really use such a machine on a single-dish telescope. And so as this next diagram, which Dario Colombo made, and now there are several versions of this, but this is good enough, basically the whole galactic plane has been done to quite a high level of detail. So in particular for the Northern Hemisphere, I would point out the Fugan survey, which you can see here. This is at almost as high a resolution as what the GBT will be capable of, 3 millimeters, and very high spectral resolution and sensitivity. So the question then, going back to this point, the question becomes, is this incremental improvement that Argus promises, while certainly good, is it really worth the effort? And so I had to wonder where Argus and the GBT can really make the greatest impact. In other words, what's the really new science that can come out of this combination at this facility? Again, in the sense of asking big questions but not necessarily having all the answers, I just wanted to put some thoughts down about where we could think about going with this instrument in the 3 millimeter band, which has its unique advantages and its unique limitations, as every instrument does. And we need to sort of optimize those in order to get the best science out of what we can do. And the thing which I kept coming back to, in my mind at least, was the radiometer equation, which I've pictorially represented here. So we have some limitation on speed, in other words, the available time that we can do, and pulling us in different directions is a wide area coverage or a large number of sources versus deep sensitivity. So in my mind, the workshop title, Wider and Deeper, is a little bit disconcerting to me, because it seems that we could either go wide or deep, but not necessarily both at the same time. So I think you have to be careful, as Yogi says, about where you're going. So writing down the radiometer equation there, you can see, and turning it around just to get the time required to achieve a particular sensitivity in terms of the RMS brightness temperature in a given velocity channel. You can figure out the amount of time you need to get where you want to go. And so as a standard number, it's 150 seconds per pixel observed on the sky to get that very high sensitivity and spectral resolution. And then, as this is all according to the Argus webpage, for a typical 0.1 degree map with the Nyquist sample pixels, we have a couple of hours to get the data, but including overheads, it's more like 5, which is a very good number for such a high quality data product. But what was surprising to me was that MOPRA could do the same thing in 10 times as much time. Now, that sounds like MOPRA's nowhere near as good as GBT, which of course it isn't. But what surprised me was that GBT has 20 times MOPRA's collecting area. So why is the GBT so slow, is my question. And so what I got from David Freya's talk yesterday was that indeed the aperture and beam efficiencies are much lower at the GBT than a MOPRA, which lowers the efficiency and the time required to reach a certain target. So the bottom line is, to get that target, you need about 500 hours per square degree at that high sensitivity level, or if you can afford to degrade those criteria somewhat, you can reduce that time requirement. But any lowering of efficiency is critically increases the time required to get to your science goals. So that's just an important thing to remember, I think. So this means that the sort of large-scale survey that some people have already started talking about seems to me a little bit prohibitive, especially if you think about the GBT site and how much 3 millimeter time is really available in a given season. And B, the result of a large area survey wouldn't be that much better. I mean, a factor of 2 or 3 is definitely better. There's no question about that. But would it really be revolutionary compared to something like the Fugen survey? These are the sort of trade-offs we have to worry about, I think. And while the sensitivity is clearly available, I think in the context of what's already been done and where Argus could make the most impact, I think preserving that sensitivity by limiting the target area to be covered, or the sample size that you want to do, is probably a good thing to keep in mind, because otherwise you degrade your revolution to something that's less revolutionary. So I just think that's kind of important. Okay, trying to hurry along here. So as an example, we faced the very same dilemma with MOPRA when it first became survey capable with its very nice back end, and different groups went in different directions, and the science was optimized in each case just to achieve the particular science goal. So there are three surveys which I'm sort of displayed here just as examples for how this works. And depending on what you're targeting, you can do good science, but you have to think about it carefully. So how do we increase the efficiency with the GBT and Argus 144? Well, on-the-fly mapping is certainly good if that's feasible without creating huge feed arm vibrations. So that's one subject to engineering limitations. That's one possibility. I don't know if Argus will be capable of frequency switching, but if that were an option, that would also be a very efficient way of observing and maximizing your time on source. But then you've got the site problem. So in other words, Greenbank, apparently, from what I can find on the web, is not as good a millimeter site as MOPRA, and MOPRA is not very good at all. Let me just reassure you about that. So at least at MOPRA, you can get a good chunk of time, a good fraction of the year available for 3 millimeter observing, whereas at Greenbank it seems quite a bit worse. So that means that weather mitigation, if your weather is not optimal, and it isn't, except for a tiny fraction of the time, you need to be able to handle the inevitable problems with marginal data. So it's not just an on-off switch where you can do something else when it starts raining, because there's lots of weather which is neither here nor there, and you're going to need judgment calls. So that makes your data reduction challenging. One thing I'd like to suggest, which we found very useful at MOPRA, was active mapping. So what I've got displayed here are some RMS maps. So this is just a measure of the RMS in the spectra for 2 different projects. We had a FAR 3 kiloparsec ARM project where we used active mapping, and there's on the left and on the right there's a CHAMP map where we use just regular OTF mapping. And the difference is that you're adapting your scanning speed in the on-the-fly mapping to respond to the conditions, the system temperature conditions dominated by the atmospheric contribution. And you can see where you can do that modification, the RMS performance is much more uniform, which of course makes your science much more uniform and robust. And this is only with adapting the mapping speed every hour or so. If it can be done in real time to speed up or slow down the data taking on the sky, I think that would make an even bigger difference, and it would actually increase your efficiency by quite a bit. Also, another idea is perhaps, which I've not seen done anywhere, but you can see in this previous CHAMP map that it's kind of a funny shape because that's where the stuff is. And you don't want to waste your time, especially if it's weak emission, on blank sky. So if there was some software engineering that could be done to allow Argus to map somewhat more arbitrary map shapes than just squares or even rectangles, that would be very helpful, I think, because then again, you can maximize your time on signal and minimize your time on blank sky. And automated observing, very important, because with any sort of large survey, or really any observing program at all, the more you can automate the mundane things like pointing checks and source selection, or if you've got a large target list and that sort of thing, you can really simplify the observing team's problem set and make it much more easier and more productive to be on the telescope and not waste time just trying to fix things. So the post-processing, I'm starting to rush through my finishing slides here. Post-processing also needs to be thought through carefully, and I know it's in the very capable hands of Mr. Rozalowski. So I'm sure some of these things, many of these things are being thought of very carefully. Combining components in sort of higher level scripts, I think, is a very good option for processing and calibration. So we've had a little success with that at MOPRA. And eventually, I think machine learning or artificial intelligence, or at least smart programs that can build in your experience and knowledge will really help with this sort of thing. Okay, and a final point is for people to work together. And I know this is obvious, but having seen where this doesn't happen, it's a little bit cringeworthy where people waste a lot of time duplicating each other and competing against each other. So please, let's not do that. Okay, so 4 ideas. So where are we going? My main takeaway from this is that Argus 144 will be really good for going deeper, but for wider, I think you have to be a little bit more careful because there's a lot that's already been done. And rather than reinventing the wheel, I think some of this prior work could be used as finder charts for the deeper stuff, which I think is scientifically a little bit more strategic. So particular ideas. So if we if we start on the smaller scale, if we bootstrap from these galactic surveys that exist and create finder charts for, say, targeted classes of dense clumps, or a set of nearby clouds where you could do a large sample of dense cores at very high resolution. There's a lot of talks that seem to be approaching these sorts of problems, and I think that's great. That would be very interesting. But again, I would point out that some important subparsec work has already been done in a lot of these other surveys, so keep your eyes out for that. One idea which I've not seen mentioned anywhere is there have been a lot of galactic plane surveys, but as far as I know, not so many off-plane galactic cloud surveys. So spurs, warped parts of the disk, the outer galaxy, etc., that kind of thing. So that might be something that Argus could be used for. And it would be very new and interesting, because then we'd be talking about lower metallicity and different sorts of clouds than what we're used to thinking about. Local group galaxies, there's a couple of talks that look like they will address that problem, so I think that's feasible as long as the field sizes aren't too big, because then you run into time requirements. And, I may well be wrong here, but it seems to me that once you get out to 10 megaparsec, things become quite hard, not least because of the small filling factors which wind up happening on resolution scales which simply don't resolve the important features. So let me try to wrap this up. This is another revised version of the radiometer equation. I think the GBT and Argus are being squeezed on the wide and deep side from existing surveys and instruments. But on the other hand, it could go in new directions, both wide and deep, as long as this was carefully thought out. And I will finish on that slide. Thank you for your attention.
Thank you, Peter. In terms of just capabilities, with the GBT, we can do frequency switching while they're doing on-the-fly mapping, and in fact, most galactic observers do it that way, and that does provide decent efficiency. We do have a question here. Oh, it's a point that's being made by one of our attendees. Another thing to think. Reason the GBT is, quote, slow is the beam is small, so you need to observe many more pixels on the sky. And based on Andy gave his talk yesterday, that you can only put the feed horns in so close together. So it's really a sparsely filled array. So you do have to get a Nyquist sample map. And with a small sparsely filled array, that takes a longer time to cover an area.
Right. If I could try to answer through audio. That's true, but at the same time, the GBT's very large collecting area means the speed goes up dramatically because of the sensitivity. So, I mean, in fact, this was one of the things, one of the ahas we had about MOPRA doing a galactic plane survey in the first place was that with a bright line like 12CO, the beam being small, quote unquote, was not a disadvantage if the telescope is large, because then you have the collecting area and you can get the sensitivity you want for the bright lines, at least, in much less time than you ever thought before. So I don't disagree with what Jens said in his comments, but I think the things like aperture efficiency and beam efficiency are what really kind of get you, because there's no way around those, because then you lose to some effectively the advantage of the larger collecting area through those lower efficiencies.
And that's why we keep pushing our surface performance the best we can do.
Very good.
And it also, it was brought up yesterday in our technical discussions that Andy was mentioning 90 gigahertz is sort of the sweet spot. We can do 110 gigahertz, we didn't 115 gigahertz, but things are starting to drop off, of course, due to the Roos equation by an exponential. So fortunately, there's a lot of interesting dense tracers in the 90 gigahertz range that might be worth pursuing.
Absolutely.